Okay, so today we are going to discuss about standing wave. Standing wave is also known as stationary wave. And this standing wave, this material will divide into two parts, which are first bond and the second is free end. In this video, you will only learn about bond end. Okay, so like I said before, today's material standing wave have two kinds, which are bond end and free end. But in this video, you will only learn about bond end, right? But before that, you have to know what is standing wave, right? So, standing wave is a wave that happens because there's superposition. But what is superposition then? Well, I'm going to demonstrate. Okay, so imagine that if you have a string like this, okay, with the end of the string have a boundary, okay, and let's say you give this string a single pulse like this, okay. This pulse or disturbance will go all the way the string and reach the boundary. When it reaches the boundary, the disturbance will not go on straight ahead, but when it meets the boundary, it will reflect it upside down, just like this. And it will travels back in the opposite direction. And in this situation, it will go on and keeps bouncing. Okay, but let's say that you didn't just give a single pulse into a string, but you gave it lots of disturbance and creating a simple harmonic wave just like this. And once again, when it meets the boundary, it will reflect it upside down just like this, okay. And this process will go on and keeps bouncing. Well, when the real wave and the reflected wave meet and interfere with one another, the superposition will occur. This is what happened to the wave. But what you see in your eyes, in your bare eyes, at first you will only see that the wave moving right to the left, right? But after the superposition happened, the wave will only go up and down, up and down, up and down, up and down, on and on. Because it just go up and down and not moving, that is why this wave is called standing wave. To differentiate between bond end and free end, if it is bond end, when the wave came and it meets the boundary, it will invert it and goes upside down, right? But while for the free end, if the wave came all the way until the string end, like this, the wave will go right side up, will returns right side up, different than bond end that goes opposite. If we gave it lot of pulse, lots of disturbance, both of these picture will happen. For bond end, if you're paying attention, at the beginning and at the end of the wave, you will find notes like this, not moving point. While for free end, you will find an anti-note at the beginning and the end of the wave. Okay? So that is the difference. Okay, moving on. So a string has an infinite number of resonant frequencies. The first possibility for a standing wave with the lowest frequency, which corresponds with the longest wavelength, it will only produce a one bump like this. This is one bump. This is the one bump along the string length, or we called it L. This one bump called fundamental frequency, with the L equals to wavelength over 2, because it is only a half of wavelength, right? Okay, so each successive harmonic has an additional node and antinode. For example, this is the second harmonic. There are 2 bumps, like this. There are 2 bumps. And for the third, there are 3, and so on. If you're paying attention, for the first harmonic, it only have 2 notes and 1 antinode. While for the second harmonic, it only have 3 notes like this and 1 antinode. That's what happened, because each successive harmonic has an additional node and antinode. Okay? Okay, so how to find the wavelength of a standing wave? Well, drawing picture will help you, but how do you create it mathematically? At first, please do remember that for bond and standing wave, at the beginning and at the end of the standing wave, you must have notes like this. This is bond end. Okay? So, what is actually the wavelength of this all 4 harmonic standing wave then? Okay, so if you can see here, the first harmonic, or the fundamental frequency that doesn't have notes in it, of the standing wave is only a half of a lambda. Remember, one wavelength, it have to go here and all the way down here and back up again into here. Okay, remember. But along this string of 10 meter length, it only have half of lambda. But the question is, how much is the 1 lambda of this wave? So the answer is, we must add the length of the first half of lambda, and we have to add it 1 more of the half of the lambda, which is 10 meters. Okay, so the conclusion is, the lambda for the first one is equals to 20 meter. But how about the second and the third and the fourth then? For the second, it is easy, because it is already shown that for the second harmonic, it is 1 length. So the answer is, for the wavelength of the second harmonic of the standing wave, it is 10 meter. Well, look at this. At the third one, we have 1 lambda here. We already have 1 lambda here, but it is added 1 more. So it will not make 1 lambda, right? But we only have to search how much is the lambda, 1 lambda of this wave. The answer is, so for this, the lambda will be 2/3 of the length. I'm going to write this. Okay, so lambda is equals to 2/3 of the length. Okay, so 2/3 of times 10, just like this. Okay, and how about the fourth then? Well, the fourth one, we can see 1 lambda here. 1 lambda of the length of the string, which is the half of it. So the lambda for the fourth harmonic with the length of the string is 10 meters. It'll be half of the L. This is half times 10, it'll be 5 meter. Okay? So the conclusion is, if you see all the patterns for this, let's say that I want to find the wavelength of the 43rd harmonic of the standing wave. Of course, you don't want to sit down and just draw all of these pictures, like your hands will get tired. So, how to manage that? You see, all of these have a pattern. Let me show you. For the first one, it have a pattern like this: 2 times 10 meters over 1, and this have also a pattern which make it 10 meters, which is 2 times 10 meters of the length divided by 2. The third one is also 2 times the length of the string divided by 4, and this is 2. 2 divided by the length of the string divided by 5. This is the pattern. So if I want to find 1/43 of a harmonic standing wave, I can just make like this.
So this is the n lambda, or the n wavelength that we want to know. It is equal to 2 times the length of the string divided by n. N is just like the first, the second, or the third wavelength that we want to know. So basically, n is really just an integer 1, 2, 3, and so on.
This is the formula to find the wavelength. We are given a question: what is the wavelength of the standing wave with 3 antinodes? Okay, first thing to do is to draw the wave. Two notes at the end. It says the wave have 3 antinodes. So I'm going to draw 3 antinodes. 1, 2, and 3, just like that.
So the next thing to do is that we have to count how many wavelengths that 3 antinodes have in a string. So this is 1 lambda, this is 1 wavelength over here, but it says that it have 3 antinodes, right? So this string will have a half more of lambda, right over here, a half more of lambda. All the way the string, we have 1.5 lambda. So we can conclude that the length of the string have 1.5 lambda, or equals to 3/2 lambda. So we can find out that the wavelength is equals to 2/3 length of the string. So this is the answer. Well, that's all for today's video regarding bond and standing wave. Hope you guys liked it, enjoy it, and learn from it. I'm very sorry for all the mistakes I made. I will see you soon. Bye!
It doesn't matter if it's true. I've got a feeling love will give us what we like.